Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at momentum equation applied to deflector. So let me show you what a deflector looks like. But before that, you can split the deflector into two types. First is called the stationary deflector, and you also have a moving deflector. Okay, now let's take a look at a stationary deflector first and see the forces that is in play and how we can relate that to momentum equation. So a deflector, as the name suggests, it deflects water. Okay, it looks something like this. Right, and it is just a stationary device that is deflecting water. So let me write here, this is a stationary deflector. Okay, and water comes from the left hand side, and I'm going to write this in blue. So water comes from the left hand side, and it will follow the shape of this deflector and deflects upward at a certain angle. And the exit angle of the water, alpha, is equal to the angle of the deflector, which is also alpha. Okay, now let's draw our control volume. And let's say that we are going to include the deflector together inside our control volume. And in order to make sure that this deflector stays in place, we're going to have two forces here, which is called Ry and also Rx. Because without Rx and Ry, this deflector would move because of the force from the water. And of course, you're going to have V1 here, that is velocity at inlet. And then you also have V2 here, which is the velocity at outlet. And one very important assumption that we make when we analyze a simple deflector like this is that we always assume that V1 equal to V2. Of course, in the real world, in the actual life, this does not happen. V2 will be slightly less than V1, but for the sake of simplicity, we can assume this at the moment. And if you notice here, I don't have my pressure force. I don't have P1A1 at inlet, and I don't have P2A2 at outlet. Why is this happening? The reason is because this deflector and also this water jet is exposed to atmosphere. So P1 and P2 is 0. So there are no pressure force in play here. And if I take the summation of the force in x direction, and let's do positive to the right, and this is equal to minus Rx. And there are no other forces. You only have Rx. And this Rx is equal to our original momentum equation, which is m dot V2 minus V1. But since this is in x direction, so it will be m dot V2x minus V1x. And this is equal to m dot V2 cos alpha. Remember that the angle here is alpha minus V1, and V1 is perfectly in x direction. So we also know that V1 equal to V2, so I can further simplify this to be m dot V1, this is cos alpha minus 1. And for the summation of force in y direction, this is even simpler. So upward is positive, and this is equal to Ry equal to m dot V2y minus V1y. And we know that at point 1, there is no y direction, so V1y is 0, and V2y is simply m dot V2 sine alpha. And V2 is equal to V1, so I can also write this as m dot V1 sine alpha. So when you have the stationary deflector, the equation for Rx and Ry to keep the deflector in place is this equation and also this equation. And I think this is quite straightforward, but after this, we are going to take a look at one example to familiarize yourself with this equation. But before that, let's take a look at moving deflectors. What does it look like? First of all, it is still a deflector, but this deflector can move to the left and to the right, depending on the direction of water. Now, let's draw an almost similar deflector. And the only difference from this deflector and the stationary deflector is you can say that this deflector is on top of wheels. So it is free to move left and right. And if we have water jet coming from the left, let's draw this in blue. And this is your water jet. And of course, this water jet is going to deflect together with the deflector. And let's say that the angle of the deflector is alpha. Now, let's take a look at what happens to the velocity component. Because when you have the jet velocity, that is the velocity of the water, this is called V1. And this deflector is moving to the right with the velocity of VB. Let me write this in purple just to differentiate it. So this moves to the right with velocity VB. And this is water from left to right at velocity V1. Now that when you have two velocities moving in the same direction, you're going to end up with a relative velocity. Now, the concept of relative velocity is very simple. For example, if you are in a car that is moving at 60 km an hour, and then you have the next car next to you that is moving at velocity of 100 km an hour, so from your perspective, the velocity of the other car should be 100 minus 60. So you are seeing that car moving at 40 km an hour. Even though the actual speed is actually 100 km an hour and your actual speed is 60 km an hour. So the difference between this velocity when it's moving in the same direction is the relative velocity. So the relative velocity here is simply V relative at point 1 equal to V1 minus VB. And if I were to draw a schematic, for example, so the total velocity here would be V1, and V1 is VB plus your VR1. So if I draw a control volume that encloses our deflector here, the velocity that goes into this control volume is actually relative velocity. It is the velocity that the deflector feels. Now, the water is coming at V1, but the deflector itself is moving at VB. So, V1 minus VB is the velocity that the deflector feels, and this is called VR1. And at exit of this control volume is called VR2. And using similar assumption that the velocity does not move when it goes through the deflector, so VR1 is still equal to VR2, which means now that VR2 is also V1 minus VB. Now, it may seem very complicated now, but when you do the example, it's going to be easier for you. And the other component that is still missing is actually the force. For the stationary deflector just now, you have Ry and Rx. Now, what about the moving deflector? So, for moving deflector, you only have one force here, which is called R. Now, I think that we have everything labeled. Let's take a look at what happens to our momentum equation when you have the moving deflector. Let's take the summation of force in x direction, positive to the right. So, this will be equal to minus Rx. Now, R will be divided into two components, that is Rx and Ry. Okay, so summation of force in x direction equal to minus Rx, and there are no other forces, there are no pressure forces, equal to the momentum in x direction. So m dot v2 minus v1. But in this problem, because we are using relative velocity, so it becomes m dot relative times v2x relative minus v1x relative. So this is m dot r times v2x relative is of course vr2, this is cos alpha, minus v1x relative is simply vr1. Okay, and we also know that vr1 equal to vr2, so this equation becomes m dot relative vr1 cos alpha minus 1. And from this equation, we know that VR1 equal to V1 minus VB. So why not I put it here? So M dot R V1 minus VB cos alpha minus 1. And that is your Rx. And what about our summation of force in Y direction? So positive is upward, equal to Ry equal to m dot r times v2yr minus v1yr. So m dot r times, what is our v2yr? And v2yr is this one. So that is vr2 sine alpha minus v1yr. There is no y direction at point 1. So this is minus 0 and this is equal to m dot r. So VR2 is equal to VR1 sine alpha, and VR1 is equal to V1 minus VB. So this is m dot r V1 minus VB times sine alpha. And finally this m dot r, and remember, m dot is simply rho times velocity times area. But for m dot r is rho times velocity. Let's say you are looking at point 1. So this is r1 times area at point 1. So just change velocity with relative velocity. When the deflector is moving, as you notice, everything is in relative. Let me highlight this here. So this is your Ry. Right, now that we have all the equation, why don't we take a look at some of the example of stationary and also moving deflectors. Now our first example, which is a stationary deflector, and it looks something like this. This is your deflector. Water coming in from the left, and we'll follow the shape of this deflector. And our alpha is 30 degree. And this water jet is actually a sheet of water, meaning that the flow area looks something like this. The dimension of this sheet of water is 2 millimeter times 400 millimeter. So this is basically a very thin sheet of water. And the mass flow rate is given to be 32 kilogram per second. And the question is asking what is the force required in order to hold the deflector stationary. So it's looking for Rx and Ry. So before everybody got confused, let me mention here that this is a stationary deflector. Now let's draw our control volume. It looks something like this. And now we can label where is our Ry and also Rx. And let me label the velocity. So this would be V1 and this would be V2. And this is 0.1 and this is 0.2. Now I think this is quite straightforward and we already have equation for this. So for stationary deflector, minus Rx is equal to m dot V1 cos alpha minus 1. Now let's copy this equation. This is minus Rx equal to m dot V1 cos alpha minus 1. And I believe only one component is missing here, which is our V1, right? So m dot equal to rho times V1 times A1 equal to 32, and rho is 1000. Velocity 1, area is simply 0.002 times 0.4 equal to 32. And our V1 turns out to be, that would be 32 divided by 0.002 divided by 0.4 divided by 1000. 40 meter per second. And now our Rx should be m dot is 32, V1 is 40, cos alpha is cos 30 minus 1. And this is equal to 40 times 32 times cos 30. That is minus 171 Newton, right? So, of course, it should be in negative because this is negative. So, Rx is 171 Newton. And that's how you solve this problem using momentum equation. But what happens to Ry? I think Ry should equal to m dot V1 sine alpha. So, Ry is equal to m dot V1 sine alpha. And this is 32. V1 is 40 times sine 30. This is equal to 30 times 40 sine 30. 640 Newton. And that will be your answer for this problem. 171 Newton to the left, which is the direction of our Rx, and 640 Newton upward, which is our direction of Ry. Now, I think this is quite a simple example. Now, let's make it a little bit more complicated by introducing a moving deflector. Okay, now let's take a look at our moving deflector. And of course, water will come from left to right. Let's use blue. And this water will follow the deflector. And this deflector is at 30-degree angle from the horizontal line. And what you have here is V1 equal to 80 meter per second. And again, this is a thin sheet of water. The dimension is 2 millimeter times 400 millimeter. And this deflector is moving to the right. This is the velocity of the body, which is 30 meter per second. Now, the question is asking for A, the force that's needed to support the deflector. So, force to support deflector. So, this is Rx and Ry. B, the question is asking for V2. Remember, we're going to end up with VR2, but the question is asking for V2. And C is the power generated by the vane. Right, so vane is actually a deflector. In certain application, we call the moving deflector vane. So from now on, let's call this vane. And because this vane has Rx and Ry, meaning that when I introduced to you earlier that this vane is supported on roller, so this is not totally accurate. So let me remove this roller here. This means that this vane could also have Rx and Ry. If I draw a roller there, it implies that this vane will move without restriction. Okay, which means that it doesn't have Rx, isn't it? But vane actually has Rx and Ry. So a little correction there. Now let's take a look at our control volume. First of all, let's draw it, and I'm going to draw it in orange. This is our control volume. And remember, this is a moving deflector. So you are going to need to find out what is the relative velocity. And then I'm going to label where is our Ry, and also what is our Rx. And in here, I know that the velocity that I need is actually VR1. So VR1 is equal to V1 minus VB. And the water exit with VR2. And we know that VR2 is equal to VR1. So it's also equal to V1 minus VB. Now let's try to find what is Rx and Ry. And I think now we are at a point where we are comfortable enough with momentum equation, so I don't have to do it step by step. Now Rx is equal to m dot r, and please do not forget the relative sign, because if you forget it here, you will forget it in your calculation, right? And this is equal to V2x relative minus V1x relative. Now let's find what is m dot r. Remember that m dot r at point 1 is equal to m dot r at point 2. So let's do point 1. So m dot r at point 1 is rho times relative velocity at point 1 times area at point 1. This is equal to 1000. Relative velocity at point 1 is V1 minus VB. That is 80 minus 30. So 80 minus 30 times A1 is 0.002 times 0.4. This is equal to 1000 times 50 times 0.002 times 0.4, 40 kilogram per second. So this is 40 kilogram per second. What is our V2x relative? V2x relative is simply VR2 cos 30. Alright, so this is VR2 cos 30 minus V1xr. So this is relative velocity at point 1 in x direction. So we only have VR1 here. So this is minus VR1. We also know that VR2 equal to VR1. So minus Rx is equal to 40 times, what is our VR1? VR1 is 80 minus 30. So this is 50 times cos 30 minus 1. And this is equal to 40 times 50 times cos 30 minus 1. Minus 268 Newton. So Rx is equal to 268 Newton. And this is actually quite a long way to do it. And if you notice, you already have this equation earlier, right? So when you are familiar with how momentum equation work, you don't necessarily have to memorize it. You only need to know how to derive it again. Right, now let's take a look at what is our Ry, because that is what our question wants. Now when we take a look at the force in y direction, okay, so Ry is equal to m dot r V2y relative minus V1y relative. And we know that m dot relative is equal to 40. And what is our 2y relative? So that's got to be VR2 sine 30. So this is VR2 sine 30. And for relative velocity at point 1 in y direction, I don't think we have it. Okay, so this is simply 0. And you end up with, and our VR2 is equal to VR1 is equal to 50. And this is 40 times 50 sine 30. This is 1000 Newton. And that is the answer for Rx and Ry. So basically, you have completed question A. And now, what about V2? To find V2, we need to draw what really happens at the exit. So the flow exit at the velocity and angle of VR2. And remember, the body is still moving to the right. So our V body is there. So this is your VB. So V2 is VR2 plus VB. And that is a vector addition. So your V2 should really be here. This is your V2. And therefore, to calculate V2, you need to resolve it into the component. So V2x is equal to VR2 cos 30 plus VB. And V2y is simply VR2 sin 30. Does it make sense? Now, if I copy this equation and solve it at the bottom, so copy and paste it here. And now we can try to solve this. So this is equal to VR2 is also VR1 and VR1 is 50 cos 30 plus VB. VB is moving to the right at 30 meter per second plus 30. And this is equal to 50 cos 30 plus 30. 73.3 meter per second. And my V2y is simply 50 sin 30. This is equal to 25 meter per second. And that is the component of V2, X component and Y component. And if I were to write this in vector form, so my V2 is equal to 73.3 meter per second to the right plus 25 meter per second in Y direction. And therefore, I believe that you have already solved question B. That is your V2. And finally, question C is asking for power generated by vane. Now, this is actually quite simple because power is simply velocity times force. So, power, let me call this W dot body equal to velocity of the body times force. But now, do you select Rx or Ry? Now, let's take a look again at the figure, right? And this body is moving to the right, meaning that it is moving in X direction. And power is only generated at the direction which the body is moving. So, the obvious choice for R here is Rx and VB is 30. Our Rx is 268. And this is equal to 30 times 268, 8040 watt. So that is all for this example. You found out what is force Rx and Ry. You found out what is V2 and you found out what is the power generated by the vane. So I hope by now you can see that the moving deflector, the way to solve it is actually almost similar with stationary deflector. The only difference is how you select the velocity. For stationary deflector, it's more straightforward, but for moving deflector, you're gonna have to use the relative velocity. So as usual, do this example again and again, and that is all from me for now, and I'll talk to you soon. Bye!